Hello, this will be a demonstration of proposition 19 from book 3 of Euclid's Elements, which states that if a straight line touches a circle and from the point of tangency a straight line is drawn perpendicular to the tangent, the center of the circle will lie on that straight line, namely the perpendicular. All we are given is the circle ABC, like so. We call that A, we call B over here, and C is here. And we have the straight line DC touching the circle ABC at point D. So let's draw that straight line. It'll look something like that. And then we draw it from point C on DE, a straight line perpendicular to DE. We're given this. I'm going to draw that down and just point C to the side. And it's perpendicular, so we'll have right angles there. What we've set out to prove is that the center of the circle ABC is somewhere on the straight line AC. For if this is not the case, then it falls on some other straight line. And we'll say for right now that this straight line is FC. Okay. We join the straight line CF. We can do that by postulate 1, obviously. Now we know that FC must be perpendicular to DE because it passes through the center. We're saying that the point F is the center. And if a straight line through the center touches a straight line tangent to a circle at the point of contact, this straight line, this radius, will be perpendicular to the tangent straight line. This is proposition 3.18, the one before this one. And because FC is perpendicular to DE, we can say that the angle FCE is a right angle, like so. And we also know that the angle ACE is a right angle. We were given that AC is perpendicular to DE, and so the angle ACE must be a right angle. And by postulate 4, that all right angles are equal to each other, we have two angles, FCE and ACE, which are both right angles. And so they must be equal to each other, so that we can say that the angle FCE is equal to the angle ACE. But we also know that the angle FCE must be less than the angle ACE, because the angle FCE is a part of the whole angle ACE. And this, by common notion 5, we know that the part is less than the whole. And so the angle FCE must simultaneously be equal to and less than AC, which is obviously absurd. And so the center of the straight line cannot fail to lie on the straight line CA. Because if it falls on any other straight line, then we end up with this contradiction. And so falling on no other straight line but CA, the center of the circle ABC must lie on the straight line AC. This being what we set out to prove, we are done with the proposition, therefore, etc. QED. This with proposition 3.18 form the whole converse of the porism of 3.16. Each partial converse is switching around certain parts of the porism in the conditional. So taking 18 and 19 together, we have a full converse to the porism of 3.16, which is pretty neat. That's all I have to say about this proposition, so I will move on to 3.20.